Alright, so in this video we're going to talk about another example problem. We have a box of mass 25 kilograms sitting on a surface that is inclined by 10 degrees. So that's what I've drawn down here. We have our box of 25 kilograms, not a very cube-shaped box, but it should be okay. And then I've drawn in the angle of inclination of 10 degrees down here. And we're given the coefficient of static friction between the box and the surface. And we want to know how much force must be applied parallel to the ramp, so along here, to just start the box moving down the incline. Alright, so since we want to apply a force to the box, we probably should sum forces on the box. So for step 1, we're going to look at the box. And step 2, we need to identify our forces. So the box is sitting on a surface, so we have the box on the force normal. And remember, we're rotating our coordinate system, so this is our y direction, and this is our x direction. Let's see, what else do we got? So we're applying a force, and that's going to be in the positive x direction. If we assume down the ramp is in the positive x. Friction is going to oppose that. So that's going to be negative x. And then we have the weight of the box, or the force due to gravity. And that's going to be positive x and negative y. So the box is going to end up help to push the box down the ramp, but it's still holding the box to the ramp with its negative x component. Alright, now we need to draw our free body diagram, and I'm going to rotate our free body diagram. So step 3 I'm going to put down here. We have a force normal in the positive y, force due to friction static, working with static. And the negative x, force applied in the positive x, and then a force due to gravity that is down here. We have force of gravity in the y, force of gravity in the x, and then our angle of inclination theta would be right there in the diagram. Alright, so when we go to our x and y equations, in the x direction we have a negative force of friction, a positive force applied, and a positive x component of our force due to gravity. And then in our y direction, we have a negative force of gravity acting in the y direction, and then the force normal. Our goal here is to find the force applied, which is in our x direction equation. We can find FGX. Remember, FGX is equal to mg sine of theta, but we don't know what the force due to friction is. We can find the force due to friction using other information supplied in the problem. So we have the coefficient of static friction, which allows us to find the force due to static friction. If we can first find the force normal, and the force normal is in the y direction. So we can make use of the idea that the force due to gravity in the y direction is equal to mg cosine of theta, remember they're switched for these, plus force normal, and it sums to 0 because it's not bouncing up and down on the ramp. So plugging in our given values, we know it's 25 kilograms the mass of the box, we know 9.8 meters per second squared, and we're taking the cosine of the angle of inclination, which is 10 degrees. That allows us to find a force normal of 249 newtons, which I then can plug back in up here to find out that the force due to friction static is equal to 121 newtons, which I will then plug in up here for the force of friction static. And that will allow me to plug in to find the force applied. Thus, remembering though that the force due to gravity x is mass times our gravitational field strength times the sine of theta, because once again we have those angles flipped because of the way our triangle is set up down here, where the y component is adjacent to the angle provided and the x component is opposite. This gives me then my final relationship that the force applied is 78.5 newtons.